Welcome all to this 17th lecture of Principles of Statistics. Today we're going to prove Theorem 2, and so this is about the inadmissibility of the maximum likelihood estimator for high dimensions, although high in this case is not very high, it's just 3 or more dimensions. And I will speak about this result, so make some remarks, and then we'll start with classification problems. Okay, so proof of Theorem 2. So prove Theorem 2. Okay, and so let me start then by computing the risk of the, the estimate that we're looking at. So this MLE, and so this is just the capital X. And this guy is very simply, we're using the mean squared error, and so, or the quadratic risk. And so, of course, this is going to be given simply by the expectation, and this is under theta of the X minus theta. So when I say, under theta, I mean the normal distribution with the theta. It means theta, and this is simply the sum from Jacob 1 to P of the expectation under theta of each of the xj's. Yeah? And then, of course, this is no more than the variance of each of the xj's, and the variance is 1 of each of them, and so then, of course, this is just P. Yeah? Although we don't need to know this P exactly, but this is the calculation. Okay, what about, we said that we want to be, so we want, well, not want to be, but so we want to show that the MLE is inadmissible, and so then how do we show this? Well, the simplest way of doing so is by finding another estimator that dominates this MLE. So we've introduced the James-Stein estimator just precisely for this purpose, and so you expect now that I compute the risk for this guy. So this is the JS and theta, and so what is this equal to? Well, it's the same expectation, but now we need to plug in the other estimator, the JS estimator. And what is this? Well, this is just simply given by this quantity. Just that, and then we center it at 0. And, we can just trivially rewrite this as x minus theta minus this p minus 2 over this x squared and x. Yeah? Okay, so let me note, by the way, that, so just as a little note, so this is given by, this is bounded by 2 times the expectation of the x minus theta squared plus p minus 2. And this would be, let's see, so this would be squared, and then and then we're going to get the expectation of 1 over this. Yeah. So why am I writing this? Well, I just want to say that this is actually finite, so that the following manipulations are actually justified. And so this is, of course, finite. Yeah. So this is certainly finite. And then this guy is also finite, by the way. So this is finite because P is greater than or equal to 3. Okay. Otherwise, what would happen is that we have, an integral that is just infinite. Yeah? So I let you sort of think about that, but this is just simple calculus. So then once we have this, and it won't come in explicitly, but I will mention it in a sec, what can we do? Well, let's just expand the square, right? This is just the obvious. And so we can expand the square, and we get, we probably want to, so p minus 2 squared, and then we get the expectation under theta of of what is going to be precisely this quantity that is similar to the previous, and we're going to get minus 2 times the product of these things, yeah? And this then would be the expectation and the theta of x minus theta transpose x divided by this quantity. Yeah. Okay, so by the way, so this is finite. So the first term is finite, by the same reasoning as before. This term is finite by the same reasoning, and so this term must be finite because that term was finite. Yeah, and so we can, essentially all these manipulations are going to be justified by these two, or the finiteness of these two quantities or very related ones. Yeah? So I guess all I want to say is that the manipulations are fine. Yeah. Okay. So let's then. Okay. So maybe let's write. So note. So note that this expectation that we've got in there. So this guy. Okay, so this is no more than the sum, yeah, from j equal 1 to p of each of the elements in here. But let me now use the Tower rule. So we're going to have the iterated expectation here, and in this case, it's going to be given by so this ej, and we're going to have the xj minus theta xj divided by this quantity here. So this is, by the way, so this is the expectation under the distribution of this xj, and and the rest of the x's or the x coordinates are it's conditional on their values. Yeah, so we wouldn't be integrating out over those, just simply over the xj distribution. Yeah? Okay, so this should be very familiar. So this quantity should be very familiar to everyone. So let me maybe write it as star j, and this is because this is in the form of what we saw in the lemma, yeah, in Stein's lemma. So let me just I guess state that. So this guy is simply going to be given by the expectation under j of xj minus theta. So this is one-dimensional, yeah, and that's fine. Times some g xj, yeah, where so where g xj is very simply given by xj divided by xj squared plus a, or maybe a constant c, okay, where for, let's say, c equal to the sum over k distinct from j of the x k's squared, yep, and so this is greater than 0, and why is that? Well, simply because the probability of this capital X being 0 is precisely 0. So it's not possible that, well, I mean, it's only in a set of events. Well, it's in an event of probability 0 that this can happen, yeah, and so we can rule it out, yeah? At least with probability 1. Okay, so we have this, and then furthermore, okay, so furthermore, what do we have? Well, we have properties of this G so that we can use the previous lemma, and so G is bounded. That's clear. That should be clear to everyone, and it's also differentiable. Okay, with derivative given, you know, very simply by this. We'll see now. So we have, you know, the derivative of the numerator. Let's see, we have this times the denominator, so we get that minus the, so 2 times xj. Yeah. And we are here. And let's see, so if we write, you know, this is very clearly given by c minus xj, that would be squared, and then c plus xj squared, and I think we need a square here. Yep. Okay, so we have this quantity, and so this is clearly saying that g prime is bounded, right? By similar arguments to what you would use in the other one, for the other term, the g, just the g rather than g prime. And this means that, so g prime is bounded, and the expectation under theta of the absolute value of the derivative is going to be, yeah, maybe rather than having theta there, we wish to have a j. So this is going to be finite. Yeah? Well, I mean, that means precisely we can use this Stein's lemma. So by Stein's lemma, okay, what we have is that the, I guess we can write it here. So it's just saying that this guy is, you know, we can apply it to this quantity now, Stein's lemma, and get that this equals the expectation under j of the x squared. So you just need to rearrange terms for this. This, yeah. Okay. Okay, so that looks good, yeah, as a quantity, because then we want to put this together with, you know, the calculations that we had, or the expression that we had in there, yeah. Okay, so what does this mean? You know, putting it all together, well, it just means that if we take the risk of this JS estimator, then, you know, firstly, we have this guy, which is just simply this guy, yeah. So this is just the risk of the MLE, okay? And we also have from, you know, from the previous calculation, so you can look it up, this term. And now we have our friend, you know, minus 2 p minus 2 of the sum over, okay, so maybe, yeah, okay, so theta, the sum from j equal 1 to p of, well, actually, so I've got it there, of precisely this quantity, yeah. Yeah. Okay, so we have this sum, and now what do we write? Well, we get that plus that, and then I guess we wish to say that, so this is a simple calculation, so we wish to say that this equals p minus 2, and this is going to be, so I guess for, okay, so the sum, you know, over these j's will give me a p in the first term. Okay, this is going to be a p, and this is the expectation under theta of this. Okay, I hope that's clear. And then the other one is just going to give me minus 2 times the expectation under theta of precisely this guy. Okay. Right, so we realized this is just p minus 2, right? So this is p minus 2 times this expectation, and so it's very, very related to this, yeah? Because we're going to get a p minus 2 squared from here, and so actually this is just rx theta minus p minus 2 squared times the expectation under theta of this quantity, right? Okay, so all we need to show is that this guy is greater or equal to 0, right? So this guy is obviously greater or equal to 0, greater than or equal to 0, and that's because, so are each of the terms, and so is the, the integrand here. So that's fine, yeah. But this wouldn't really prove dominance, so we still need to find some thetas for which this term is strictly greater than 0, and this is actually very simple to show. So in fact, this expectation, which is the only potentially problematic bit, so this is strictly 0, okay, and this is for all theta, and this is because, for example, for example, in that we could be showing this in very different ways. This, you can write this as an integral, right, over the whole of RP of, 1 over this norm squared, and then taking into account the normal distribution of that guy. But what we can do is directly bound below that integral that we are sort of imagining, and so then here you're going to get, just erase this, I'm not too happy with it. So then what we're going to do is just to, as I was saying, do this for some C bar, if you like, okay? And we get just the same integrand that we would have got. And let me call this phi, the density of the standard normal, yeah? So this is something we've used in the past already. So I shouldn't be using capital letters here. I should just be using lowercase, yeah. Minus theta, yeah, and dx. All right, so now that we have this, we can further bound this below by C bar to the -2. Okay, so that's a bit of a strange number, but that's what it is. And then the probability, which is going to be, by the way, the infinite product probability, but we're not going to write it all out. So this is going to be the probability of this norm of the capital X being greater than or equal to, excuse me, not greater than, but less than epsilon. Okay, so I mean this is clearly greater than 0, yeah, and this is for all theta in our parameter space. So in this case it would be oh, and by the way, also for any C bar on the natural numbers, yeah. Well, not on the natural numbers, on the positive natural numbers, yeah. Let me just write here for clarity. C bar greater than 0. Yeah. Okay, so so if we have this, then what it means is that we have this strict positivity, and so if we have this strict positivity, then it means that our delta JS theta is actually strictly dominated all the time for any theta by this guy. Okay, so we have this and we've shown it essentially, and so now what we want to talk about, well, let me make some remarks. Okay, so first of all, and so the very first one is that, let's see, some remarks. The very first one is that not only the James-Steins estimator dominates the MLE, but there are more. Yeah, there are many more, in fact. So the MLE is actually dominated by many more estimators, including following, okay, and So this is just a slight generalization of the one we've just seen. So this is 1 minus C P minus 2 divided by this quantity. Okay. So including this, and this is for C in 0, 2. And by the way, so let me maybe point out. So however, so this guy, James Stein, dominates. These for all C human. So we open here. I was writing, but this should be open 0, 2. Yeah. Okay. So that's good news. Still, we found a nice estimator, but from now on, let me talk a bit about drawbacks of this James Stein estimator. So let's have a second remark, and let's say that it can be shown that the James Stein estimator is dominated, or well, let's say that is inadmissible. Okay, it's inadmissible. So of course, never good news. And let me give an example of a dominating rule. Dominated. For instance, by precisely, this James Stein estimator, but with a slight modification. So let's say, this guy, because this is a positive part, and so this is quite a well-known, well, at least, something that is known when you study, something that you should study when you study a bit of decision theory. Okay, so I've taken the positive part. Yeah, that's important. Okay. So then 3. Okay, what can we say? Well, I guess what we want to say is that despite nice qualities, not all are nice. So despite this JS dominates the MLE, we still get that this maximal risk, okay, that should be capital, yeah, okay. So despite that I was saying, if we look at the risk of this estimator, okay, then it turns out that it is the same as that of the MLE. Okay, so it's not really better from a minimax point of view, although of course, inadmissibility is something that we do not want. Yeah? So 4. Yet another drawback, and this is actually probably the most important in practice. So while, whilst this guy dominates, well, okay, let's just write it out. The MLE, so let me just shorten things. The distribution of this guy is unknown. Yeah? So then if it is unknown, it means that there will be no obvious There's no obvious way to, or how to use this James-Stein estimator for other inferential procedures. Yeah, so the one we've seen certainly works. Inferential procedures. But then the question is, what about in the future? I mean, can we use this? Okay, so this means that in practice, so including, sorry, why did I write second? So that should be a 4. Yeah. Okay. So so joined with 3, it means that the MLE may and probably is still preferred in practice. Okay, so let me now give a couple of more remarks that maybe getting, close to, well, I mean, they are non-examinable in some sense, but it's just like some of these comments are just interesting to know. Yeah, I wouldn't ask you to prove, some of these claims, but you should still be familiar with some of these ideas, because that's just general knowledge for statistics. Okay, so let me now mention, I haven't mentioned this so far, and is that this James-Stein estimator is a very particular one. So you should, I'm sure you're thinking, how on earth did this guy come up with this so that it has smaller mean squared error? Well, so this guy and, these guys that we were talking about are what is called shrinkage estimators. Shrinkage estimators. Okay, so what do I mean by this? Well, let's see. So the expectation of not under theta, but under maybe okay, so that's right, theta equals 0 of this 1 minus p minus 2 x squared is no more than 1 minus p minus 2 of the expectation under this of this here. Yeah. And so then this is just no more than 1 minus p minus 2 divided by precisely p minus 2. Yeah. So this is, okay, maybe let's say p minus 2 here. And this is now 0. Yeah. Okay, so this happens. Okay, so what is going on is that in expectation, the shrinkage, it's not light. Actually, it will be quite aggressive, and what is going to happen? So it biases. So it biases the MLE. Okay, maybe just slightly, but anyway, but so by essentially, as I'm saying, so essentially shrinking. Essentially shrinking its coordinates. Yeah. Okay, and then you say, well, okay, so if you bias coordinates, then what's happening with the variance? Or, a different question is, is this really doing the right thing? If you're biasing it, then, does it depend on the parameter theta? Well, yes. I mean, the amount of bias depends on the parameter theta, but it turns out that this, the loss that you get from this bias is, even in cases in which the theta is not close to the origin, is going to be compensated by the decrease in the variance that there will be. Yeah. So let me write that. So this may not sound very reasonable or promising. And this, of course, for parameters that are away from the origin, because then if you're shrinking towards the origin and you're away from it, then what's the point, right? One would think. So this may not sound very reasonable if the parameter is far from the origin, and this is, by the way, all very informal. Because I mean, it could be that you know, use only one coordinate that is non-zero, and it's actually very large, and then the rest are zero. Yeah, so that's not very far from the origin, but you've already shrunk. You know, I mean, these you know, they will benefit from this. Okay, so but even for these cases, okay, and this is important. So even for these cases, it reduces the variance which is, by the way, the main, I guess, the main source of mean squared error. Okay, so remember that we can split the mean squared error as the sum of bias and the variance. So the main source is going to be the mean squared error, because essentially, so even when you have this, well, when you have these independent random variables, then the mean squared, the variance is going to be proportional to the number of elements, and so of course, you know, you have that this will be the main source of MSE, especially in high dimensions. And so even for this case, it reduces the variance significantly enough to reduce the MC, yeah. Overall. Okay. And so, by the way, this is a common phenomenon. I'm talking about the fact that you can introduce some bias, and actually, you know, you will increase a bit of the variance. You can introduce a bit of bias and reduce the variance in such a way that the mean squared error, the overall value, is lowered. Yeah. So there's a common phenomenon in high or infinite dimensional or dimensions, and I mean, so the bias variance trade-off. You must be hearing about in other courses, or that you will very soon. I mean, this is not really examinable, at least not in terms of you having to remember things. So there's a common here, and by the way, also 3 is present. Okay, 3, 4. So I think it's 4. Okay. Okay, so 4 is still usually present, yeah. So what do I mean? This is I just mean whenever we try to shrink an estimator and do this trick of the high variance trade-off, you still have that essentially the limiting properties in terms of distributions of the estimators are not really going to be very nice. Yeah? And in fact, this is an active area of research. As in, for high or infinite dimensional problems, and once you find a shrinkage estimator, then can you find the limiting distributions, or if not, what do you do? Yeah, so these things are active research in many of the sort of most well-known problems in statistics. Okay, so let me now talk a bit about James Stein in a different view. So what we're going to say is that this guy is what is called the empirical or an empirical Bayes estimator. So this is an empirical Bayes estimator. And what do I mean by this? Well, let me just explain. So let's take, the setting that we're considering. So we have this, so if x given mu, or in this case, maybe a theta, and this theta, or this guy is distributed according to this here. So we have an identity matrix, and the theta we want it to be distributed according to a normal distribution, multivariate of p dimension, and with mean 0 and covariance given by this identity matrix time a constant. Then what do we get? Excuse me. So we get, with sigma squared known, so let's assume that it is known, then we have that theta given x is going to be distributed according to normal distribution with distribution, sigma squared divided by sigma squared plus 1 times the x, and then sigma squared divided by sigma squared plus 1, and then the identity. So that you can edit it as an exercise. So then it implies that Bayes, Bayes estimator for theta is, let's call it theta hat, theta bar, is going to be sigma squared divided by sigma squared plus 1 x, which is of course 1 minus 1 over sigma squared plus 1. Yeah. Yes. Okay, so if we have this, well, then we're done. But if the sigma squared is unknown, then we cannot use this estimator. So if sigma squared unknown, then we can substitute it by, in this case, empirical. Okay. By an empirical estimator. I mean, not that there are not empirical estimators. Yeah, I mean, an estimator is just measurable function of data, and so of course it will be empirical. Yeah. But I guess I just want to emphasize that it is empirical because that's what it gives the name to empirical Bayes. Yeah. So we're using a Bayes estimator, and we plug in something empirical, so we get an empirical Bayes estimator. Yeah. Okay, so this guy is going to then, or I guess, yeah, okay, so let's look at the marginal for the capital X, because that will be somehow very related to sigma squared. So you know, X is going to be marginally, so if we integrate out, so if we, you know, take these guys and integrate out the theta, then what we get is that this is just normal distribution with mean 0 and variance given by sigma squared plus 1 and the identity. Yeah. So we can take as an estimator the following, or well, maybe actually before taking the X estimator, let me say that, you know, this guy obviously is going to be distributed according to a chi-squared distribution with some constant coming out of it, and this means that if we take the expectation, and this is under yeah, okay, so if we take the expectation of this guy, okay, this is going to be precisely, so there's a common calculation to do, so this is going to be the 1 over sigma squared plus 1, and so we can plug in, right, we can plug in this guy. And this is, by the way, so I think I'm missing something, so this, yeah, I should be writing p minus 2. Okay. All right. Yeah. Okay, that sounds good. And so this is what I'm saying, that you can plug this in then into, you know, into the Bayes estimator, and so, well, let's say and this JS is what's called the empirical Bayes estimator, or an empirical Bayes estimator. Okay, it can be taken very different paths. Okay, and so let me lastly remark that this is a very common way of constructing shrinkage estimators in practice. Okay, but it doesn't mean that we'll be able to avoid the issues with the lack of knowledge of the distribution properties, yeah, of the distributions. Okay, so classification problems. Okay, so this is a finite decision problem. And so, you know, a finite decision problem of practical importance is this classification. Let me just shorten it as classification, class, sorry. So for instance, we have, you know, medical diagnosis, or image recognition, which of course has a myriad of applications, many more applications here. Yeah? Okay. So we're going to we're going to concentrate, just for simplicity, on the binary case. So let us concentrate on binary classification. Okay, and so we assume that there are two underlying populations. Two fixed populations. X, according to some F1, and X according to some F2, and both of them on, this calligraphic X that we've been talking about, so the sample space. And we observe, so also assume that we observe X equal to some small x, yeah? Okay, so we wish to decide, or to find, well, I guess decide, with the ultimate goal of finding, so we wish to decide what population gave rise to this lowercase x. Yeah. Okay, so to decide this, let us introduce a few concepts. So a binary, these are more general concepts. So let me just write this binary in brackets. So binary classification rule, let's call it delta, is given by a region. Yeah? And we can call this calligraphic R, and of course it's a subset of this calligraphic X, such that, so this guy has to satisfy that, this delta that, was not really dependent on anything. Well, if we write what we're writing, then it really is quite dependent on these things. Also, this will be 1 if X is in the calligraphic R, and 2 otherwise, so if it's not. Okay. And then what we can now do is just to work out the probabilities of misclassification so that we can build the base classification risk. Yeah? So the probabilities of the I guess, of misclassifying X when it comes from F1 is simply the probability of getting, of choosing 2, given the 1 was true, and also given the choice of calligraphic R, which is no more than the integral of this guy over the complement of the F1, okay? And that should be clear, right? So we assume we have, a sample from F1, and then we integrate over the region that is not really going to give us the correct classification. And this is now, well, I can write this out simply also as this, in case you're more comfortable with this. And for X from F2 is, the obvious. So it's this guy here. And this is now the integral over R of f2. Yeah. Why did I write that? Sorry, shouldn't be that. So it should be calligraphic R. Yeah. Okay. So now let's introduce some priors so that we can define the risk, the base risk. So if pi is Q1, which belongs to 0, 1, so just as any probability, and we get the and we get the Q2 being 1 minus Q1. Well, let me say that these are priors. Okay, so these are prior distributions, or prior probabilities for 1 and f2, so that's just fine, respectively. Then what we get is that the base classification risk, let me underline that, is precisely the sum, this is the risk, this is just the usual capital R. So this guy at this delta that has been defined through a region, we can write theta 1, and then the other one is so plus, sorry, has an extra bracket, so plus R at the classification rule, that theta 2 times pi of theta 2, and this theta dependence, in here can be quite complicated, but we won't go into details of that. So this is just simply the expectation and the pi of the this risk here. This is an integral over the theta, so the pi will integrate over the theta. Yeah? Or, said differently, what we have here is no more than this R pi of delta R, which is something we've sort of seen in the past. Okay, so what do we conclude from this? Well, we conclude that we're in, So what do we conclude? We conclude that we're in the usual setting of base, or the decision theory. Yeah. Okay, so in the general, let me shorten it as GRAL, decision theory framework. Okay, so now how do we act on this to get a nice decision rule? So given x equal to some small x, then Bayes' theorem tells us we need Bayes' theorem to be talking about all these things. So Bayes' rule or theorem gives what are called Bayes factors, given by the following. So this is pi j of conditions on this guy, and this is very simply going to be given by this fj at the x times q1 divided by f1 of x q1 plus f2 of x q2. Yeah, should be clear. Okay, so this is for j equal 1 and 2, and so that the decision is made in the following sense. So we classify X into group 1 if we get the following. Oh, excuse me. If it's just the obvious, so if the factor for group 1 is actually greater than 1, yeah? Sorry, well, the factor is greater than the other, yeah? So that's just the obvious thing. So this is what I'm saying. So this is just that F1 at X, Q1 is greater strictly than F2 at X at the same X in Q2. Yeah? Okay. Let's maybe just for completeness say and into group 2 otherwise. Yeah? Turns out that the resulting rule is base. Okay, so we're done for today, and I hope that you enjoyed the lecture and that you're here again for the next one.